Okay, so thank you very much for still coming. So let me very quickly recall the notation and the definition for what we were doing yesterday. So I was dealing with diffeomorphisms of the circle with commuting diffeomorphisms in these classes of differentiability, C1 plus bounded variation, which is a class which is needed for the validity of the Danjois theorem. This is why it is called also the Danjois class. And in many cases, we have to go to this differentiability class, which is slightly smaller than C2, C1 plus absolutely continuous, which means that the derivative is absolutely continuous. So there is a second derivative, which is well defined almost everywhere, and it is in L1. And the point of view that we were exploring yesterday is that in this case, the variation of the logarithm of the derivative is by definition the integral of the absolute value of the derivative of the logarithm of the derivative. And this expression is very nice. This is the affine derivative, d2 over d. So this expression can be, this integral here can be talked about, can be thought as the L1 norm of the affine derivative. And the chain rule for the affine derivative is this formula here. And a good interpretation for this is that this is a cocycle in the space L1. So here there is a change of variables. So this is still isometric in the space L1. And this is very, very important. Okay? This will be crucial in some of the arguments today. And I was discussing something related to this, which was a very important notion that appeared in the computations, so, which is what I call the asymptotic variation. So remember that the variation of the logarithm of the derivative is not invariant under conjugacy, and if we look for something which is invariant under conjugacy, it is very natural to take the asymptotic version of that, which means that I will take the limit as n goes to infinite of the variation of the logarithm of the iterate divided by n. And again, in the particular case where we are in class C1 plus absolutely continuous, this is equal to the this limit here, which can be interpreted as the growth of the yes?
So when you say it's an L1 cocycle, what kind of relation it means it satisfies?
So this is the cocycle relation. And the point is that you can think more algebraically. So when you compose with G and multiply by the derivative of G, this is an isometric action in the space L1. So this is a cocycle with respect to the natural action in the L1 space. Okay? So let me just say that the classical derivative, so the chain rule is dfg equals to the product, but it's better to take the logarithm. So the logarithm of the derivative is the sum of the logarithm of the derivative. But here you have to compose with G, I think. Yes? So if you are dealing with C1 diffeomorphism, this can be interpreted as a cocycle in the space of continuous functions, because this is a change of variable in the space of continuous functions. It doesn't change the subnorm. And when you take derivatives here, you get that relation. But that relation is well behaved in the space L1, because in that space, this change of variables there is an isometry. Okay? Okay, and with that formula there, you can interpret the asymptotic variation of the growth as the linear growth of this cocycle, which is the affine derivative. So this is the affine derivative of the nth iterate of f divided by n. And this number was our obstruction in order to perform the conjugacy for a single diffeomorphism to the rotation for a single diffeomorphism to the identity in the case of the interval, and it works more or less the same for the case of commuting diffeomorphisms. This is why this is so nice. Okay, so we were studying the behavior of this function. Okay, we saw, I will recall that in a few minutes, that for the case of the circle, this is very well behaved. But for the case of the interval, this is, the situation is totally different. And this was somehow discussed by Hélène in her talk yesterday. So I will consider the space of diffeomorphism of the interval with no fixed point in the interior and for which the endpoints are parabolic. So I put the hypothesis of parabolicity here because if you have a hyperbolic fixed points, immediately the asymptotic variation explodes because the hyperbolicity will grow exponentially along the iterates, so the variation will be linear along the iterates. And there is a nice issue here. So in this space D, the asymptotic variation is a continuous function. So if you perturb a little bit the map, but you stay in this space D of diffeomorphisms with no fixed point in the interior, then the value of the asymptotic variation will change a little bit. But actually, the asymptotic variation can be defined for any diffeomorphism. And this function, the asymptotic variation, is not continuous. It is only upper semi-continuous. This follows more or less from the definition, but it is not continuous. And the example to show discontinuity is really very nice. So it goes more or less like this. So I will not go into the details with the relation here between the asymptotic variation and the matter invariant that I discussed yesterday, but I will just explain how to create positive asymptotic variation, starting from something that has vanishing asymptotic variation. So if you start with a diffeomorphism, which is, again, very boring from the point of view of topological dynamics, let's say that it pushes everything to the right, the endpoints are parabolic. Say, for instance, if you have a diffeomorphism like this, that this is a parabolic element in the Möbius in the group of Möbius transformation, and you pick a fundamental domain and you do some perturbation inside the fundamental domain, and then you define G as F times this perturbation, then if the variation of the asymptotic variation of F vanishes, then immediately the asymptotic variation of G is positive. Okay? This can be proven by hand. I mean, this can be proven in full generality just by playing with the derivatives and so on. But what is behind that is that an F like this must have a trivial matter invariant, and this kind of perturbation is the classical one in order to create non-trivial matter invariant. So we are passing from trivial matter invariant to a non-trivial invariant. And because of the relation between the matter invariant and the asymptotic variation, we have this. But again, this can be proved by hand. And somehow the matter invariant here is the diffeomorphism H, put it in the right coordinates. Okay? Now, it turns out that, well, this is true when the perturbation is supported on a single fundamental domain. Because if you support the perturbation on, say, one fundamental domain here and one fundamental domain here, you can somehow do something here, starting with F, and you can do something which destroys the perturbation that you did here. And this way, you get, again, trivial matter invariant. Okay? And now the idea is very nice. So the idea is trying to play with this with a diffeomorphism like this. So G is going to be F composed with H and with H tilde, and trying to look at the closure of the set of diffeomorphisms like this, and in the end to get something with positive asymptotic variation. So, somehow when in the limit, so the picture of F is something like so this is the original F, and then there is the perturbation. Let me denote it by G, and the idea is starting conjugating G so that in the end you get a tangency in the interior. So there is starting from F, G is obtained as a perturbation on a fundamental domain here and on a fundamental domain here. And the idea now is taking a sequence of conjugates of G so that it becomes more tangent and more tangent to the identity. And in the end, there is a tangency to the identity. And there is a single perturbation on the left and a single perturbation on the right. And because of that, there is non-trivial matter invariant here and non-trivial invariant here, so that in the end there is a positive asymptotic variation on both sides. Okay? And there is a nice motivation for this. There is a very nice paper by Dimitri Dolgopiat, mostly on dynamics, which is related to the case which is prior to the situation of the tangency. And the title is very nice. It's a very nice paper as well. So there are a lot of very interesting computation about decay of correlations of maps like this. And it is inspiring this very famous song and movie, Apelito a Kiss. But I prefer to use my own cultural reference. So this is the situation when there is the tangency. And believe me, he was a very popular singer in the 80s. He's from Spain, Diango. But the metaphor here is very, very, it applies very well. So this is the reason why the asymptotic variation explodes. This is because of the tangency. And what I think that is very interesting here, and again, I benefit of the presence of Christian here, is that the explosion, the discontinuity of the asymptotic variation arises in the closure of the conjugacy class of the single diffeomorphism. Okay? And actually, I was thinking about whether this is a general fact or not. So there are many words, for instance, on discontinuity of Lyapunov exponents, and I think that nobody worry about whether this discontinuity may arise in the closure of a single diffeomorphism, in the closure of the conjugacy class of a single diffeomorphism, or in the closure of the conjugacy class of a cocycle. So I think that it would be interesting to produce examples in this spirit as well in this setting. Okay, so we should be careful when looking at the asymptotic variation because it is discontinuous. Okay, it is just upper semi-continuous. And now that you wake up, I hope, let me come back to what we were doing. So we were trying to connect using conjugacies an action of two commuting diffeomorphisms to the action of the corresponding rotations for the case of the circle, or to the identity for the case of the interval. Anyway. And for that, there was this magic formula, which means that if I take F and G, so two commuting maps in the Danjois class, and I conjugate by this Hn, then there was a miracle here that the variation of the logarithm of the conjugate of F is smaller or equal than the variation of the logarithm of the derivative of F to the n divided by n, and the same is true for G. Okay? Okay, so in case this expression goes to 0, which means that the asymptotic variation vanishes, then we are done. We can connect the action of the original action to the action by rotations. Okay? And the problem was now to detect the obstruction to having vanishing asymptotic variation or not. And there was this first result for the case of maps with irrational rotation number that says that in class C1 plus absolutely continuous, the asymptotic variation vanishes. Okay?
In your formula there, is the example that the total variation of asymptotic variation for f is not 0 and the commutation g?
That's a very good question. That's a very good question. So this was it is in my slide. So this is very, very interesting, because if you have two commuting diffeomorphism, it is not obvious that whether if one has positive asymptotic variation, the other cannot have it, and so on. But actually, the theorem says that in the case of irrational rotation number, they are both equal to 0. And for the case of the interval, we will see it is an indirect consequence of the relation with the matter invariant that they have to be simultaneously 0, in case one of them is 0. But it doesn't follow from the definition. It's something, for me, this is still surprising, I mean. Okay, thank you. And so I was trying to explain that yesterday, and I explained half of the proof. And I say, well, there is some version of the definition of the asymptotic variations that allows completing the proof. So let me remember what I proved yesterday was that if f is a C1 plus absolutely continuous diffeomorphism of the circle with irrational rotation number, then there exists a sequence of functions in L1 such that the coboundaries associated to this converge to the affine derivative of f in L1. Okay? This is what I proved yesterday using the Ham-Banach argument. And now I will explain why this implies that the asymptotic variation of f vanishes. Okay? I claim that this was a direct consequence of this, but I will do the computation in order to show something. But this is actually totally general. So again, if you think of this as a cocycle, and it's a totally general fact that if a cocycle can be approximated by coboundaries, then the growth of the cocycle is sublinear. This is what is behind here. Okay, but I will do the computation. So up to an epsilon, I can fix. So given epsilon, I can fix a function u in L1 such that the coboundary associated to u is epsilon close in L1 to the affine derivative. And now I will compose this with, say, f to the I, and I will multiply by the derivative. Okay? And this is still epsilon close to this. And the reason is that this composition here, this change of variable, is an isometry in L1. So you keep the same epsilon there. And then I will take the sum from I equal to 0 to, say, n minus 1, and I will divide by n. And, well, this is still epsilon close to this. Okay, this is just the triangular inequality in L1. And this is a telescopic sum. So in this telescopic sum, what you get in the end is that u composed with f to the n times dfn minus u divided by n is epsilon close to this sum here, 1 over n, this sum. But because of the chain rule of the affine derivative, this is the affine derivative of f to the n. This is just the chain rule. Okay? And now if you compute the norm, so what you get is that 1 over n d2 over d of f to the n is smaller or equal than this epsilon plus this. And here I use the triangular inequality again, and I have this. And the norm of this is the L1 norm. The L1 norm of this is the same as the L1 norm of u. So when n goes to infinite, this goes to 0. So the lim sup, if you wish, as n goes to infinite of this, is smaller or equal than epsilon. And this is true for every epsilon, because for any given epsilon, I can find the function u for which this is true. Okay? So in the end, what I get is that this limit vanishes, which is the same as saying that the asymptotic variation vanishes. Okay? So this is how the proof goes. But again, the only thing what I use here is that the affine derivative is a cocycle, and that this cocycle can be approximated by coboundaries. This is the setting. And I wanted to
Where did you use the rotation number?
I used the rotation number in the Ham-Banach trick yesterday, because at a key step I used the ergodicity with respect to the Lebesgue measure, which is the theorem of Katok and Hermann. Mm-hmm. So to prove this. Okay, and well, I will not go into the details, but this computation allows doing many other things. For instance, together with Michele Tristino, we use this kind of computations to reprove something which is very important in the approach of Michel-Hermann to his theorem of conjugacy, which is totally general. So again, one thing which is very important here is that I am not distinguishing the case of Diophantine rotation number and Julian rotation number. This is totally general. It is so elementary and very general. And this is also true for any rotation number which is irrational, is that if you take an f, and if you take the powers corresponding to the approximation by rational numbers, then f to the power qn converges to the identity in C1 topology, whenever f is a C2 diffeomorphism, which is hard to prove actually. It requires a lot of work in the paper of Michel-Hermann, and doing this kind of computations, it becomes very, very natural. And actually, well, we were able to extend it to the case of C1 plus absolutely continuous diffeomorphism. But this is not the important point. The important point is that the proof is much simpler and I think more conceptual. Okay, so this is the case of the circle. I will call it the case of the real case of the circle because there is an irrational rotation number. Yes?
Does it matter how you approximate the irrational number with rationals?
Yes.
Do they have to converge fast, or it should be
No. This is the sequence of approximation that appears in the continuous function expansion. Okay. Okay, so this was the case of the circle, and again, I call it the genuine case of the sequence, because it's the case where there is an irrational rotation number. And this is totally solved by this kind of arguments whenever we are in class C1 plus absolutely continuous. And the problem now is the case of the interval. And because of the discontinuity of the asymptotic variation, because it is non-trivial in general, and this was what I discussed yesterday, in this space D, one way to restate the relation with the matter invariant without passing through the matter invariant is the following. So in this space D of diffeomorphism with no interior fixed point and parabolic endpoints, a diffeomorphism has vanishing asymptotic variation. Sorry, I put. So by the way, in my first paper, I used this name, asymptotic distortion, and it was a very bad name, and Ellen then after that correct the name, and now it is called asymptotic variation. So this is why there is this name, which is the wrong name, asymptotic distortion, but the right name is asymptotic variation. And the theorem says that the vanishing of this variation, asymptotic variation, holds non-vanishing holds only in the case of a diffeomorphism for which the C1 centralizer is small. Namely, it is infinite cyclic. Okay? This is what is given by the relation between the asymptotic variation and the matter invariant and the matter theory. Okay? And here there is this consequence that you asked before. If you take two diffeomorphisms of the interval which are commuting, then the vanishing of B infinite has to be simultaneous, which again doesn't follow from the definition. It's a kind of surprise. You cannot have a diffeomorphism with positive asymptotic variation which commutes with a diffeomorphism with vanishing asymptotic variation. Okay? And we don't know how to prove that directly without passing through the matter invariant. Okay, and
so this result is when you don't have fixed point in the interior.
When we don't have fixed point.
What happens there?
This is.
Because if you permute intervals, you preserve the matter invariant by conjugacy, by C1 conjugacy.
So yes.
So the accumulation, there is no trouble at the accumulation?
So very good point. So it depends whether you are thinking on the interval or on the circle. You can do on the interval. Yeah. Well, on the interval, you cannot permute the intervals because otherwise you will have two commuting diffeomorphisms, one with fixed points and the other without fixed points, and this contradicts Koppel's lemma. You see? So in case you have a, because we are in the class where Koppel's lemma holds. So this is actually a very big difference between, so the statements are the same in class C1 and C1 plus absolutely continuous, but the situations are rather different. Because here we are in a very rigid situation, and in C1 we are in a very flexible situation. So the connectedness results are totally different, actually. The same statement, but. Yes, it holds in C1 plus bounded variation, actually. Yes. Yeah. Okay. So again, this is I state this in this way because this is what we need in order to prove the connectedness theorem. So in the case where we cannot perform this trick of conjugacy by these magic maps Hn, we know how is the structure of the centralizer. Okay, so we have two problems in order to conclude the proof, more or less. The first thing is that I was dealing with the case where the endpoints of the interval were parabolic. But actually, we may have a hyperbolic fixed points for an action. And we need to know what to do. And a natural idea would be to use these maps that I already show that actually work in C1 topology, x to the alpha. These are only homeomorphisms. They are not differentiable at the origin. Well, they are not diffeomorphism at the origin. But one can do some conjugacies around hyperbolic fixed points. And this can be done in an equivariant way. And that should be OK, hopefully. And the other problem is that, OK, let's assume that all parabolic point, all fixed points that will appear in the action will be parabolic. And we are in the case of rational rotation numbers, so essentially we're in the case of the interval. And suppose that for the case of the interval, we will concentrate on a single fundamental domain for the action, which means that, not fundamental domain, but connected component of the complementary set of the global fixed points. So we are somehow in the space D, and we would like to use the structure theorem about the asymptotic variation in that case. If it vanishes, we can do the conjugacy. If it doesn't vanish, then we know that the centralizer is cyclic. So we know that although we are dealing with two commuting diffeomorphisms, they are both the power of the same diffeomorphism. And I will deform the single diffeomorphism to get to the identity in the end. Okay, so these two ideas are very natural. However, there are serious problems with both ideas. And I will concentrate on, I will start by concentrating on the problem related to two, which means that, so let me explain why there is a problem here. Okay, so, and well, again, so during my lectures, I state the case of two commuting diffeomorphisms, but actually this applies to any number of commuting diffeomorphisms, so any CD action. So we are in the situation where CD is generated by D maps, and there is positive asymptotic variation, and because of this Mather structure theorem, we know that they are all powers of the same map. And what we want to do, again, is to deform this map to the diagonal, just following the affine path of the graph. Okay, so it looks very, very, very well, but the problem is that this works inside an interval which is in the complement of the set of global fixed points. But there might be many intervals like that. And you would like to perform the deformation on each of these intervals. So I am thinking about the following situation. So I have, for instance, I have two maps, F and G. They commute. But they have infinitely many global fixed points. And I would like to apply this argument here inside each of these intervals. But if I want to apply this argument on each of these intervals, then I would like to apply the argument simultaneously. And for that, I will need to keep some control on the deformation. And the key problem here is that although the diffeomorphism must converge to the identity in C2 topology in very small intervals, the generator, capital F, is not necessarily close to the identity. And this is a general phenomenon for diffeomorphism of the interval. You may have a diffeomorphism which is very close to the identity, say in C2 topology, which has a square root, and for which the square root is far away from the identity. So that if you start doing this procedure here and you deform this capital F, then you may be very quickly far away from the identity. And so you cannot use this argument infinitely many times in a simultaneous way because you will lose continuity of the deformation. Okay? And this is a crucial problem that only arises in the case of infinitely many fixed points. But we would like to have a theorem which is totally general, which also covers this case. Okay? And how to solve this problem? Sorry?
Is there any simple example, at least pictorial, to see something that the roots grow in distance?
Well, this is why I put the names here. So Sir Gerard, what he did was to build, correct me, Ellen, if I'm wrong, to build a diffeomorphism for which there is no square root. It doesn't have a square root in the same differentiability class. The square root is only C1 but not C2. Okay? And this is somehow reminiscent of the fact that for the diffeomorphisms that have a square root, there is no control between the original diffeomorphism and the square root. Otherwise, somehow, this is the heuristic view, is that there will be a square root for every diffeomorphism, which is not the case. But actually, one can produce examples by hand just by playing with the maybe you know how to do it explicitly. Otherwise, one can work with the cohomological equation.
I don't know whether when you try to construct such an example of a diffeomorphism that doesn't have a square root, it is constructed by an infinite number of deformations. If you stop at some, you don't go all the way, but you stop, what you get is a diffeomorphism with a huge square root, and if you go until the end, you have no square root.
Yes, and Hélène and Christian, they know very well how to play this game with not only with the square root, but with many other times. So in this situation, it may happen, for instance, for two commutative diffeomorphisms that there is an f such that f is equal to capital F to the square, g is f to the capital F to the cube. They are both close to identity, but the capital F is far away from the identity. Okay, this can be done. I think that if you play, if you look for a capital F for which this is true, this is a kind of cohomological equation that you can implement and doing some perturbation on half of the fundamental domains. You can get this by hand. Okay, but this is a well-known abstraction to perform this kind of methods. And to solve this problem, there is a kind of miracle again, a trick. And the trick uses again the asymptotic variation. Because you know, capital F is far away from the identity, but the asymptotic variation has to be small because of the homogeneity property of the asymptotic variation. So if you have, for instance, capital F equals to f to the k, and the asymptotic variation of f is small, well, what? 2, 3. Yep. Thank you. And the asymptotic variation of this is small. This is also very small because of the homogeneity property. So the asymptotic variation of f is equal to the asymptotic variation of capital F to the k, which is k times, the asymptotic variation of capital F. So that the asymptotic variation of capital F equals to the asymptotic variation of small f divided by k. So if this is small, again, this is also small. But this is the asymptotic variation, not the variation of the logarithm of the derivative. So the idea is that capital F is far away from the identity because it is in the ground coordinates. Because in the asymptotic coordinates, it should be small. Okay? And remember that there was an alternative approach to the asymptotic variation. So the alternative approach was the asymptotic variation of some map, let me denote it by H, is equal to the infimum. No, this is not a good. The variation of the logarithm of the derivative of the conjugates of the map. There was this formula yesterday. Okay? And this suggests the fact that since this is small because of this, then there should be some change of coordinates where the capital F becomes small again, and where you can perform this deformation trick in a controlled way. Okay? This is the idea to solve the problem. And in terms of formulas, what you do is remember the magic conjugacy, the HN, which was taking the two maps and taking this mean of the derivatives and so on. Well, from the point of view of computations, you consider, so if you start with F and G, then you add this capital F and you construct an HN that incorporates this capital F in the formula. Okay? So this is going to be the integral between 0 and x of the root of order n to the cube of the fi gj fl of x. The product of this. I, j, l from 0 to n minus 1, and you normalize from 0 to 1. And you use this sequence of conjugators. And this sequence of conjugators allows to simultaneously smoothing F, G, and capital F so that they become close to the identity. And when you are close enough to the identity, then you perform the deformation trick. Okay? And again, this is a miracle. It works. It works because of this, all this stuff of, this algebraic stuff of chain rules and so on. Okay? This is how this problem is solved. And this is, again, this is a trick that only works in class C1 plus absolutely continuous. This is a serious abstraction to go further in differentiability. Okay? We don't know how to perform such a trick in class C2, for instance. Okay? And this is one of the reasons why we only have connectedness and not path connectedness in the C2 setting. Okay? And I think this is also
is defined for each interval.
for each interval.
And if you all of them, it converges. So what is important is that the sequence of conjugate actions converge. So maybe you are doing something on each of the intervals. Maybe if you pass together this HN defined on a single interval with the HN defined on another interval, it doesn't fit actually. But when you look at the conjugate actions, they fit pretty well. Okay? The HN here may have different derivatives at the endpoints than the other ones. Yeah, but the capital F depends on the interval. So when you move from one interval to another one, you need to use another capital F. But then the estimates are not on the on this. The estimates have to be performed on the conjugate actions, and it works pretty well. See, so when again, there are a lot of tricks in this.
The capital F changing means that they are all forwarded.
Yes, that's true. That's true. Okay, it's a trick. We know it's a trick, but it works, and we are very happy because it works. Okay, but it's a trick. So this is this is the abstraction to go further in differentiability class to class C2, and I think this is more or less one of the problems that you found when dealing in the C infinite category as well, and this is known to be a very serious problem. Okay. It is difficult to perform deformation on infinitely many fixed intervals simultaneously. And the other, okay. The other problem is a kind of very unexpected problem.
So I was I think that the first day I was cheating a little bit, saying that if you perform these conjugacies with this map, with a map of the form of this, then it works well, because actually this is not the case. It works pretty well in the C1 case. There is no problem with that because the C1 topology is very easy to control. But if you go to C1 plus absolutely continuous, C1 plus boundary variation, C2, then there is no control. Okay, so we cannot do things that way. But the point is that, again, there is a very big difference between C1 and C2 when you have hyperbolic fixed points. The difference is that there is this classical theorem by Stenberg. I think there is only one error. Okay. So there is this theorem by Stenberg, which was improved by Yokos, again in his volume of asterisk, that says that if you have a hyperbolic fixed point for a map, one-dimensional map, then it is linearizable, which means that there is a, if you are in class C2, then there is a C2 change of coordinates that transforms the germ into the linear germ, which is not true in class C1. Okay, this is known since the work of Stenberg as well. So he gives a very clever example in his paper, and then he proves the linearization theorem, a weak form of the linearization theorem, and Yokos reproves the theorem, saying that actually the conjugacy has the same differentiability class, at least in class C2, and also this is true in class C1 plus alpha for any positive alpha. This has been known to the community for many times, but now we are very happy because there is a great proof by Catherine Mann and Maxime Wolf I think it is an appendix to your paper where you really needed this version of the Stenberg theorem, and this goes through more or less the same idea of the proof of Yokos using some fixed point theorem and so on. Okay. So instead of doing computations with the original action conjugated by this, our idea was to, we know how to deal with this hyperbolic fixed point. First of all, because we know how to localize them. So if there is hyperbolic fixed point, then the orbit has to be finite. And then the idea was to do not worry about them because they are linearizable. So we can perform some, we are actually in the affine case, at least on a neighborhood of such a point, and then we can deform along the group of affine transformations and so on. But the very big problem is that this linearization theorem is not true not only in C1 category. It is totally false in the class we are dealing with, C1 plus absolutely continuous. And this was another kind of nightmare for us for a couple of years, because we really didn't know what to do. Okay, and we discovered that there are a lot of counterexamples to Stenberg linearization theorem in the Danjois class and in the C1 plus absolutely continuous class. And actually, we wrote a paper on that only to study this phenomenon, which holds not only for diffeomorphism, it also holds for flows. And let me give you a kind of exercise which is very concrete. And we were very amazed to discover that this was true, because this is something very, very explicit. Okay? This is not the example of Stenberg, but this is actually easier than the example that appears in the paper of Stenberg. If you take the linear flow and you conjugate by this map H, well, this map H is not even Lipschitz, but the conjugate flow is still C1, and actually this C1 plus absolutely continuous. Okay, and one can build a lot of examples like this. Okay, and actually one can prove that every C1 germ of hyperbolic diffeomorphism can be approximated. I think can be put in a one-parameter family where all the diffeomorphisms in the family are non-linearizable. Yes, non-linearizable. Actually, you can prescribe the behavior of the linearization. It may happen that the linearization is continued but not Lipschitz, or Lipschitz but not C1, or C1 but not absolutely continuous, and so on. You can really prescribe almost everything, and this is very explicit actually. So we were dealing with this problem, and I will not speak about how to solve this problem, because it's a little bit technical, but there is a solution for this. There is a very nice connected lemma that was found by Hélène last year that allows solving this problem, but actually what we need to do is to change the strategy of the proof. So this is my view of the strategy of the proof, but this is not exactly how the proof goes because of this problem. And the only thing that I wanted to say is that this is the reason why there are 2 papers on arXiv, and the first one will remain unpublished, because in the first one we needed to impose the condition that the action were C2 in order to have this linearization theorem and to being able to deform through the affine flow. And it doesn't give the result in full generality. And this is our preprint in this year, actually, the last version, where we avoid this problem. And the first one is the paper we wrote on the problem of linearization of hyperbolic even vector fields in dimension 1 in low differentiability classes. Okay? And to finish, let me just say that in our paper there is also an appendix by Theo Vidot with a very short and nice proof of this fact, which is somehow folklore, but for which we couldn't find a good reference. No, there is a good reference. There is this paper by the guy who studied the, but we discovered after that, Cohen, yeah. But this is a very concrete example showing that the Danjois group is not a topological group with the canonical distance inside. And there is a very nice paper by Cohen that claims that something much stronger actually happens in this group. But here there is a very, very, very precise example showing this. And I wanted to finish with this because the technical problem happening here also appears in our proof of the connectedness. So we are not able, so there were 2 instances where we really need to use C1 plus absolutely continuous and not only C1 plus bounded variation. The first one was, for the case of the circle, the vanishing of the asymptotic variation, which is not true in the Danjois class because of the mother homomorphism. And in the case of the interval, there is, at some point, there is a technical lemma which is crucial, which doesn't work in the C1 plus bounded variation topology. And the reason is closely related to this. So again, we are not able to prove the path connectedness of the space of commuting diffeomorphisms in the Danjois class. Not even the connectedness, I think, Hélène. I don't remember. But we were interested in path connectedness. So we are far away from proving path connectedness. The topology of C1 plus bounded variation is very special. It's something very, very difficult to handle because it goes outside the space L1 if you reach from this point of view. Okay, I think I am done. Thank you very much.
Questions?
So the cocycles you mentioned, are these some, what kind of, is that like measurable cocycle for cohomology, or what kind of cocycle is it?
So for me, okay, I don't.
Because you were saying in the space of L1 functions and there's some sort of
Okay.
isometric action.
Okay, let me try to say this. So you have G is a group of diffeomorphism of the circle with some regularity. Then G acts isometrically on some Banach spaces. Isometrically means the, okay, let me first consider the linear action. So, for instance, it acts on the space of continuous function of the circle and in the space of L1 functions of the circle. So, if you are in class C1. So here the action is just, you take a function here and you just change coordinates. And I think that you have to take an inverse here, but okay. And the action on the L1 space is to change coordinates in L1. Okay? And the cocycle relation are cocycle relation with respect to these isometric representations, if you wish. Okay? So with respect to the first representation, there is this logarithm of the derivative, you see? So the logarithm of the derivative, again. So you map f into the logarithm of the derivative of f, and the relation, this one, is nothing but the fact that the cocycle of the product is the sum of the cocycle, but with the twist corresponding to the isometric action. Okay? And the relation with the second derivative, the affine derivative, is again is the same as saying that the cocycle with respect to the composition is the sum of the two cocycles. But now the action is the isometric action in L1. Okay? And it is, well, for us, it is really crucial to think things this way. Okay? There is a third cocycle, but we don't know how to do nothing with that. It's the Schwarzian derivative. Yeah, you can interpret the Schwarzian derivative as a cocycle as well. But there are serious problems to integrate the Schwarzian derivative and so on. So we would like to pass from C2 differentiability to higher differentiability using the Schwarzian derivative cocycle, but so far we were not able to do that. Mm-hmm.
I actually have a question. Does the Sternberg or Yakut's linearization theorem hold in higher dimensions?
When there is no resonance.
There's no?
Resonance between the multipliers, yes.
I see.
Mm-hmm. Yes. This is Grobman, but for the case of the flows. Yeah.
It has to be at least C2?
I don't know exactly what is the best version in higher dimensions. I know that the version of Grobman is in C infinite regularity, no? And there are versions in finite regularity, but I think that there is a little loss of differentiability for the conjugated map. But there is a lot of literature on that. Mm-hmm. But I don't know exactly what is the best version. I read a paper on that a couple of years ago, which was published a couple of years ago. So I think that the problem is not still completely solved. What is the best regularity even in dimension 2?
Any other question? Well, if not, let's thank Anders for this wonderful mini course.